Hello, my name is Mitya Khmelyak, and this is Developing a Computer Graphics Course with a Game Development Engine, where we explain how we transitioned an introductory computer graphics class from using standard graphics APIs to a game development engine. Let's start with some premises. Traditionally, computer graphics classes use standard graphics APIs for practical coursework. These same graphics APIs, however, recently evolved towards being high-performance APIs. They are closer to hardware. At the same time, however, game development engines have become full-fledged IDEs. So, if we compare them, current graphics APIs benefit software developers who build graphics engines and so on, but they are much more complex. They have a much steeper learning curve that they used to. GDEs have become extensive programming tools. They provide integrated development environments. They have computing components, scene modeling, image rendering, and so on. So, because of this increasing divide between the difficulty in learning graphics APIs compared to GDEs, GDEs are more interesting for teaching. They have a less steep learning curve, and at the same time they still allow programmer access to graphics APIs and shader-based GPU graphics programming. If we look at the history about teaching computer graphics and how it evolved through the ACM IEEE computing curricula, in the 1991 edition, at the time there was no ubiquitous API and very little dedicated hardware, there was only one computer graphics class listed in the curricula, and it included a little bit of everything. Curricula 2001, by that time, 3D graphics APIs and specialized hardware had become standardized and widespread. There were 11 classes listed in the graphics and visual computing area of the curricula. There was still no programmable GPU though. All that changed between 2001 and 2013, where affordable programmable GPUs and related APIs caused classes to change. And the basic rendering class, according to the curricula 2013, included rendering with shader-based API. And so, this is how we changed from 2001, what you see on the right, to 2013, what you see on the left. On the right, we can see an example where we draw a single triangle using OpenGL in a fixed pipeline. It takes a few lines of code and all the rest is setting up. Of course, on the right side, most of that code is also setting up the API. However, it takes hundreds of lines of code to set it up, and it's still just to draw a single triangle. But that's what we have adapted in those years, and that's how also standard computer graphics textbooks had changed to include shader programming. But now, since the last curricula, these APIs have changed again, maybe even more drastically. Direct3D, Metal, Vulkan, all these now provide a lower level of hardware abstraction, reduced overhead multi-threading capabilities, and they required hundreds of lines of code to set up just to draw that simple triangle. So the question is, what do? We either don't change and we keep using standard shader-based APIs from before 2014, or we rework our class to use the current APIs, Direct3D 12 and so on, devoting in the class additional time to cover architecture topics, CPU, GPU, and so on. We could, of course, write an entire software framework based on the current APIs, and we could present that architecture in an overview, but we could just use a GDE as a software framework, and the GDE does all that work for us. We still have to prepare most new course material. There are no standard textbooks, as far as I know, that use a GDE to teach computer graphics. Now, there are several criteria that we have used to decide about GDEs, and you can read them in the paper, but they're based on a presentation that was done at ITSE in 2017. And all these criteria are satisfied by GDEs. I'm going to just list them: learning curve, popularity, available programming languages. I would like to stop on this one for a little bit. GDEs, it's true, use a very specific programming language, C#, which is typically not used in computer science education. But at the same time, as IDEs, they are fully object-oriented, and that is not like the graphics APIs on which they're based. They are fully object-oriented because in GDEs, individual scripts are connected to specific objects in a graphics scene. And that provides a simpler navigation through a project. Each individual script is shorter. Debugging becomes quite a bit different because it requires also understanding these connections, hierarchies, and so on. Other properties such as cross-platform development, stability, community, documentation, affordability, they all are in favor of GDEs. Now let's take a look at just a few examples that we have used in our class since we have transitioned to GDEs. We have followed closely examples and topics from previous OpenGL-based editions of the class, both from the fixed pipeline first and then the ones that we taught with the programmable pipeline. We chose topics that we could use by exposing certain parts of the GDE. So starting from lab assignments. In lab assignments, we begin with general GDE concepts, and for that, fortunately, we don't have to prepare new projects, new assignments for labs, because there are lots of tutorials available for GDEs. Where it becomes more specific is where we provide activities such as this one that we are showing here, where we draw a robot arm, taken that model from the first OpenGL programming textbook. And we implement it in the GDE, and we, this way, teach geometry, relationship between geometric components and transformations, and the hierarchy, both of transformations and the components. Now, to go into more complex examples, let's take a look at a problem set that involves point line geometry. In this case, again, we have geometric components that are prepared in the GDE, and they connect to scripts where students compute the correct geometrical relationships and provide, like in this case, the normal to a line segment, which is then used to compute the closest point on a line to an external point. These are utility functions that then students use in the subsequent assignments. And to conclude, another problem set example, in this case, it is about implementing an interactive spline. We start in 2D and then we have the same assignment in 3D. In the first case, we ask students to implement this on the CPU. So that's maybe not as realistic, but it covers all the concepts that are required to understand how to approximate a curve with a succession of points. And then we bring it over to the GPU, and we have students program the vertex shader so that it processes each vertex one at a time according to the geometry they learned in the previous example. We can access the shaders from the GDE in a much simpler manner than if we had to program the entire support structure. Now, to conclude, I would like to thank, first of all the students who took this class since we transitioned to the GDEs in spring 2019, the first edition, and in spring 2020, which had an unexpected also move to online teaching. And finally, I would like to thank Holly Zhang, who is the co-author of the current paper at ITSE 2020, and she also co-authored the previous poster that we presented on the same topic at SIGSE 2020. And I would like to thank Rajin Shankar, who helped with implementing all these problem sets and redesigned them in Unity. Both of them had completed the same computer graphics class in spring 2018 when it was still based on OpenGL ES. And thank you all